Not experiment 2 just yet. Experiment 2, we might finish that one section on the paper. No, experiment 3 next week. Next week. I already talked about it a little bit, but just let me re-emphasize. Here we're going to collect our experimental data. So we have the hot gas, the cold gas. The gas was air. And then we collected the experimental volume, the hot and the cold. And then we're going to use Charles' law to calculate the volume that the gas should have contracted according to Charles' law. And then we're going to compare it. So this is the experimental cold volume, and then we're going to calculate the theoretical cold volume. The theoretical cold volume from Charles' law. And then we're going to calculate the percent error, the difference between these two. And the percent error calculation is going to be the experimental, this one, minus the theoretical, this one, divided by the theoretical. So it goes experimental minus theoretical divided by theoretical times 100%. And that gives us the percent error here. Hopefully it comes out close, but we'll see how close. It comes out. In this calculations section, just show one representative calculation, just so I could see what like conversion factors or whatever. No conversions, I think, in this, but to see how you did your calculation. So just one representative, either trial 1 or trial 2, or you can do both. But at least one, so I can see the equations that you used and the numbers. There's some additional calculations here. This is Charles' law with degree C. Normally we don't use Charles' law with degree C. Right? We use Charles' law with, if we use degree C, we have to have a correction here. And so we can calculate what the correction term is, x. And you already know what x is, because if we need to use Kelvin, then the correction for Celsius to Kelvin would be plus 273. So x should be 273, but what we can do is we can calculate it experimentally. So we know what the temperature in Celsius is, we know what the volume, and then this is the hot, this is the cold, and then solve this equation for x using some algebra. And then we'll get it for trial 1, show one representative calculation here, and then repeat it, the calculation for trial 2. And hopefully both of these come out to 273 or 273.15. Which would be more precise. That would go here. Right? We expect it to be 273 because that's what we're supposed to correct it by. But let's see how our data aligns with that. We're not going to calculate a percent error. We could do a percent error here, but we're not. The next thing we're going to do is a graph. So when we do a graph, there's going to be a title, graphical determination of absolute zero. On the y-axis, we have the volume in milliliters. So it goes from 0 to 600 plus. And on the x-axis, we have the temperature. The temperature here goes from minus 350. Is minus 350 even possible? This is an impossible temperature. How about minus 300? What's the lowest Celsius temperature you can have? It's not 0. You can get sub-zero. Negative 273. So the lowest possible temperature theoretically is minus 273, because after minus 273, then all motion stops. And so this is going to be the limit here. Of course, with experimental data, there's errors associated with it. And so what we're going to do is we're going to make two plots for trial 1. Trial 1, the hot started around 100, maybe 100 plus, and however many milliliters the apparatus was, let's say around here. And the cold was around, 25? And so we're going to put a data point here. When you do a data point, normally on a hand-drawn graph, there are different ways you could do it, but one of the most common ways is you make an X. And the center of the X is the data point, and then you circle it. If you make an X and then circle it, it's easy to see. Whereas if you make just a dot, sometimes the dot is difficult to see depending on how big the dot is, and where the center of the dot is might be difficult to see as well. And when you write a line through the dot, it's further can obscure the data point. And so we want something that isn't easily obscured by the line. And so we'll put data point here, and then the cold water with the cold volume here. And so we have two data points. So the two data points are going to define a straight line. And so we're just going to draw a straight line through this and see where it hits. You know, maybe it'll be a little low, maybe it'll be a little higher, maybe it might be right on. So let's see where it comes out. It's hard, though, because these two data points are kind of close to one another, so just small errors in this will change the slope significantly. Whereas if we have the data points more spread out, you know, small errors here are going to have less of an impact here. But, you know, the data is the data that we got, so we'll just go with that. And so you're going to do one line for trial 1. Where it intercepts here, you'll have to read the temperature. And so this goes 250 to 300 negative. So this would be 260, 270, 280. Or what is it? How many boxes? 260, 270, 280, 290, 300. So this goes by 10 degrees C increments. So we should be able to pinpoint the temperature to the nearest degree Celsius. So let's take a look. And so for trial 1, draw a line at the intercept here, read the temperature, and then just write it here where it intercepts. And then for trial 2, it might, you know, it might overlay. So if it overlays, you might want to do it in a different color or different line style. Different line style would be maybe dashed or bold or different color. And we'll do trial 2 on the same graph and see where that intersects. You know, in theory, they should overlap. They should coincide, but in practice, no, there's going to be experimental error. Now, experimental error, like I said before, a small experimental error here could throw off the slope considerably there. All right, once we figure out the intercept, you know, you'll write them down on the graph here, and then you'll rewrite them up here on the report sheet. Oh, shoot. So trial 1, write the intersect here, intercept. Trial 2, the same thing, intercept. What's the expected x-intercept? Minus 273. So let's see how close we get. So that's a hand plot that you're going to make here. And then just turn that in. Experiment 4 we're not going to do this semester. It's an interesting experiment. It's the percent water in an unknown hydrated salt. So this is a hydrate that we looked at before, copper 2 sulfate pentahydrate. The name. We have other hydrates too. Barium chloride can't hold that much water. So for barium chloride, it's a dihydrate. Sodium carbonate can hold even more water. Sodium carbonate is a, what do we call this? Tenhydrate or decahydrate. So sodium carbonate decahydrate is the name. We could figure out this. You know, when we see a formula like this, the formula is the atom ratio or the dozen ratio or the mole ratio. And so one way to analyze these salts is if we don't know how much water is in there, because these are all what we call up to capacity. In other words, we call these saturated with water vapor. However, they might not be. There could be some empty spaces in the crystal lattice that haven't had water. What we say is have water bind to those or to squeeze in to that lattice site. And so we don't know how much water. This is the max, but it could have less. And so one thing we can do is we can analyze it. So one way of analyzing these salts is we throw it in an oven and dry it. So what you do is you weigh it before and then you weigh it after. When you weigh it after, the only thing that's missing is the water. And so if you heat the oven up to about 100 degrees C, the water is going to vaporize out of those, what we call, we don't call them crevices or nooks. You know what we call them in the crystal? You think, oh, okay, they're stuck in these little crevices or nooks in the crystal lattice. But what we call them are holes. And so these water molecules are stuck in these holes, so we can dry them out of those holes by just heating it out. The copper and the sulfate, we need a lot more temperature to dry those off, but the waters we can dry off with not too much temperature. And so we dry it. And then we weigh it. From the mass difference, we can get the grams of water that we've driven off. And from grams of water, we can figure out moles of water. And once we get the moles of water, then we can figure out how many grams of salt we have and then calculate how many moles of salt. And so here we have 1 mole of salt, 5 moles of water. So we get a 1 to 5 ratio. Here we have a 1 to 2 ratio, mole ratio between salt and water. Here we have a 1 to 10 mole ratio. And so it's pretty easy to calculate the mole ratio once we have all the masses. And all we need is a molar mass in order to do that. So this is analysis of hydrated salts here. Here's heating it to drive off the water, moisture. That's the mole ratio. We could also do the percent water in the hydrate as well. That's experiment 4, which we're skipping. Then we're going to experiment 5, which we're doing today. I was expecting the lab to be set up for experiment 5, 7, etc. But we only have 5. I don't see the others. So you aren't going to need your goggles today. Hopefully they'll have it set up next time. Experiment 5 is just a demo experiment. So I want to talk about electricity and electric circuits. When we think about electricity, what comes to mind? What is electricity? Electrons? Electrons moving? Yeah. Heat, we usually think of like thermal, when things get hot, heat, thermal. Heat is a transfer of kinetic energy. So if you have a hot object, you have lots of kinetic energy. And if you touch a hot object, that kinetic energy gets transferred to you, which would be a colder object. But electricity is not the transfer of kinetic energy. The electricity is the transfer of electrons. So here I have an electric circuit here, and so we're looking at we're going to look at the movement of electrons here. And so there's a plug here. There's a ground. And then there's a hot and a neutral. The black is hot, the white is neutral, and the ground is just for safety. But if I plug this in here, then the electrons will want to flow. They'll want to flow through the circuit. However, this black, if you look at this black one, it's connected to this piece of copper here, and the white one is connected to this opposite piece of copper over here. And we call these pieces of copper metal electrodes. You know, it's just some piece of metal that conducts. It doesn't even have to be metal to be called an electrode, but this is it. Now, the electrons want to go from, let's say, here to there, but there's a gap. Do you see this air gap here? There's a gap. And so, so we got to look. The situation is the electrons can flow through the metal, copper, because the wires are made out of copper here. But when it hits the air, then there's going to be a problem. And so to overcome this gap, do you know what we need? Well, do you know what the voltage here is out of the plug? The voltage is like 120 volts, let's say. 120 volts average, which they call RMS. The peak voltage could be higher, like 130 volts peak. But 130 volts, does that sound like a lot? Well, it could give you quite a shock, but it's not a lot, because in order to jump this air gap, do you know what kind of voltage we need? The voltage is the force pushing or pulling the electrons through the circuit. We need a much higher voltage. In order to jump a gap this size, we'd need about, not 300 volts isn't enough. We'd need about, no, more. Yeah, 1,000 more. Maybe about 2,000 volts. You know, and so when you see a lightning bolt is jumping a huge gap in the air. So a lightning bolt is going as electrons going through the air, and the voltage there is extremely large. A voltage is, what is a voltage? A voltage is an imbalance of charge. And so on one end you have it positively charged, a lack of electrons. On another end you have it negatively charged, an excess of electrons. And if that voltage gets large enough, the electrons are going to jump the gap, you know, from the negative to the positive. You see this with like static electricity. If you walk across a carpet with like tennis shoes or something, and then you grab the door handle, has that ever happened to you? You get a little shock. You know, you're just building up too much static electricity. And the same thing here is if the voltage gets higher and higher, then it can jump the air gap. But for us, it's not, because this voltage is not high enough to do that. And so I'm going to plug this in, and I don't see a little lightning bolt there jumping across. And so this is called an open circuit. An open circuit, it's not closed because electrons can't flow through it from one wire to the other. And so I could close the circuit using different things. The first thing I'm going to use to close the circuit is a piece of metal here. This is steel. Steel's made up mostly of iron. It's not stainless. Oh, actually, this might be stainless steel. It looks pretty good still. A little bit of rust. But this is probably stainless steel. Still mostly iron. But I'm going to use this, and then I'm going to use this to close the gap, or close the circuit. And so let's see. Do you think it'll close it? Yeah. You see? All right. So this iron. And so what we're looking at is electrical conductivity. And metals are really good electrical conductors. And so if we look at something like iron, what's the symbol for iron? Fe. This is solid. That's a really good conductor of electricity. And in other words, if I have a piece of iron like this, the electrons can freely move through here. A good conductor is going to allow for the flow of electrons. In other words, something like iron is a good conductor because metals, and in general, metals are good conductors. Because they have loosely held electrons that have mobility. What type of mobility? Well, the type of mobility that we want is going from point x1 to point x2. What kind of mobility is that? Yeah. Translational mobility. So let's talk a little bit about the structure of iron. And so iron is what we call a metallic solid or metallic crystal. Crystals just have well-ordered arrangements of atoms, whereas non-crystalline substances, there's some disorder in the arrangement. And so this metallic solid just consists of a lattice of iron atoms. These are neutral. And this is unlike things like oxygen. Oxygen consists of molecules of O2, but when I look at this lattice of iron atoms, do you see molecules of iron in there? Like Fe2 or Fe3 or Fe4 or no, it's just a lattice. Okay, and what happens is this is like an empty room, and the electrons can just flow right through this lattice like this. And there is very little what we call resistance. And so let's take a look at electrical conductivity in more detail. The electrons are flowing through like an empty room. Versus like a crowded room. Well, we'll talk more about these kind of analogies in just a moment. But electrical conductivity depends on three things. That is, the flow of electrons, which is the electrical conductivity, is going to depend on three things: mu, n, and z. Electrical conductivity is given this symbol sigma. And the units of sigma are like the semiconductor firm Siemens. And so the conductivity is given in terms of Siemens. Mu, this sigma, this is mu. We use mu for micro, but in this context, it's not micro. Mu is being used as a measure of mobility. And when we're thinking about mobility, we're thinking about mobility of, in this case, the electrons. N refers to the number of electrons, or in this, they don't have to be electrons, as we'll see shortly. And Z refers to the charge. So I'm just going to leave it number and charge. So when we describe this, we need to use some quantum mechanics. What was quantum mechanics again? The theory. And so we're going to use some theory to describe it. But the quantum mechanics, the theory is a little bit more complicated. We typically use something called band theory. Band theory comes from quantum mechanics. And it's just quantum mechanical theory. Band theory is just that, but it's just a specific application of it. In band theory, we look at things like metals, semiconductors, and insulators. So metals have high electrical conductivity, so sigma's big. Semiconductors have low electrical conductivity, so sigma's small. And insulators should have no electrical conductivity, so sigma should be 0 or close to 0 for that. But band theory is a bit more complicated than what we want, so we're going to come up with a simple cartoon model. And so this is going to be the cartoonish model of band theory for metals. And that would be called the electron C model. Which is a very simplified version of our band theory. In the electron C model, we look at the iron atoms. There's a nucleus here in the center of each iron atom, which I'll represent as this little dot here. Now, when we think about electricity, electricity doesn't have to be electrons. You know, electricity, the origin of the name comes from electrons, but it doesn't have to be electrons because we could have positive particles rather than negative particles transporting the electricity. That is, when I set up this apparatus here, one of these electrodes becomes positive, the other one becomes negative due to the power supply. And the electrons are going to jump from the negative to the positive. But if I have a positive particle, it would jump from the positive to the negative, and it would still transport charge. And so that would be electricity. So what can happen here is the nucleus. What is the charge on the nucleus? Positive. And so I have a positive nucleus here. And so that could transport electricity. And so I have a positive nucleus, and I have a lot of nuclei. And a piece of iron, 55, 56 grams of iron is a mole. That's a huge number of iron atoms. That's less than 56 grams, though, but still a huge number. But the problem with nuclei, do nuclei have translational mobility? Can the atoms translate here? No, the atoms can't. Now, one of the characteristics of an electron is electrons in metals are loosely held. And so the electrons can move through the iron, like this. And so the way people visualize the electron C model is that the electrons are like the ocean here, able to flow through, and the atoms are like the pier pilings. So if you look at like the pier, Redondo Beach pier, the pilings stuck in the ground are immobile. They don't have translational motion, but the water around them does. And so the electrons are like the water around the pier pilings. And this is the electron C model for metals. Now, even though the atoms here don't have translational motion, they do have what kind of motion? Yeah, since they're spherical, we don't really think of vibrational because there's no like moment of inertia. So we would say they would have vibrational. They have vibrational motion. And if the atoms are vibrating, does the electron have a clean path through? The more the atoms vibrate, the more what? The more resistance we end up with. And the more resistance we have, the less conductivity we have. So inversely proportional to conductivity is something that we give the symbol omega to. And omega is the resistance. And the units of resistance are ohms. And so the more resistance, the lower the conductivity, the less resistance, the higher the conductivity. So hot metal, does hot metal have higher conductivity or lower conductivity? Hot. So if I increase the temperature, what's going to happen to the conductivity? If you increase the temperature, you're going to get more vibrations. If you have more vibrations, is the electron going to have an easier time or a more difficult time going across? What do you think? More difficult. So if I increase the temperature, I'm increasing the vibrations. If I increase the vibrations, then the electron is going to have to take a more convoluted path through the metal. And so the conductivity goes down, the resistance goes up. Resistance has the units ohms. If I decrease the temperature, then what's going to happen? Conductivity goes up, resistance goes down. And for metals, eventually the vibrations get so small that the electrons have a straight path. It's like an empty hallway. If the electrons are going through an empty hallway or empty room, then there's very little resistance. And so when you get the vibrations low enough, then the electrons will go straight through. And then we get something called superconductivity. And so eventually at a certain temperature, when the vibrations get so little, we'll get superconductivity at low enough temperatures. Sorry. At the limit. And so what does superconduct mean? It means that we can transport electricity with no energy loss. So there have been ideas, like for example, one idea was to put a whole bunch of solar panels in the Sahara Desert or something like that. Have you heard of that? They want to put a whole bunch of solar panels in the Sahara Desert, but what they have to do is nobody lives, or not that many people live there. What they want to do is they want to transport the electricity that's generated from North Africa to Europe. But the problem is when they calculate how much energy is lost in transporting the electricity from North Africa to Europe, it's not worth it anymore. You know, it's going to cost too much energy. And so it's not going to be beneficial. So even though the Sahara has lots of sun and Europe doesn't have nearly as much, that would fail unless they can transport the electricity using superconductors. And so this has been a big topic for a long time because transport of electricity, even across the U.S., you're going to lose a lot of the energy due to resistance, due to losses. And so the problem is that how cold do you have to get? With a lot of superconductors, you have to get it extremely cold. One of the superconductors that I worked with, you have to cool it using liquid helium. Liquid helium goes down to 4 Kelvin. And liquid helium isn't cheap. Liquid helium's really expensive and it vaporizes off very fast. So we had liquid helium, and then to prevent losing liquid helium, you surround it with another jacket of liquid nitrogen. And the liquid nitrogen's constantly boiling off. So you have to refill the liquid nitrogen every day because you're losing so much of it to boiling, evaporation. And then it's insulated a little bit, not that much. And so it becomes very expensive. And so this is something that people are looking at. So anyway, this has excellent conductivity. This is a piece of iron. But it could have better conductivity if we cooled it down. But we aren't. Room temperature is plenty enough. And electrons can flow through the metal. Okay, well, let's take a look at the next. And tell me what you think. Distilled water. Should it have high conductivity, low conductivity, or no conductivity? Low? Uh-huh.
Because you could say that it's low because it's made out of nothing, but it also has like an ion. It also forms ion bonds.
Okay, let's talk about electrical conductivity. Electrical conductivity can happen with any charged particle. It could be negative or it could be positive. And so I talked about superconductors, but we also have ionic conductors too. And so we could have charged ions. So for example, here, one electrode is going to be negative. The other electrode, this is a chunk of metal, or it doesn't even have to be a metal. We can make electrodes out of anything that conducts electricity. So what are some things that conduct electricity that aren't metals? Can you name anything that conducts electricity that isn't a metal? Oh.
Water.
Water? What else? Uh-huh.
It's like elementary, but a potato.
A potato? Okay. Potato can. Water, we'll have to answer that in a minute. Uh-huh. Yeah. Yeah, your body. Potatoes, well, what we have in potatoes, there's no metal in potatoes, but they can conduct electricity. They can conduct electricity because there are ions in there. And so these ions can transport charge here. And so we could have negative ions and positive ions, and those result in ionic conductors. Ionic conductors, we use the exact same equation here. There has to be some mobility of the ions, there has to be some number of ions, and there has to be a charge on the ions, and then we'll get electrical conductivity. We can even have something called superionic conductors. Superionic conductors, you don't want to cool to 0 or near 0 Kelvin. The reason you don't want to cool these down too much is because we need the ions to move. So there has to be some thermal energy for the ions to move. Superionic conductors, what they have is they have these channels. Let me show you here. So in the superionic phase, there could be vibrations here, but the ions will have channels, these free channels. These are like empty hallways that the ions can travel through. And be that way. The situation with these superionic conductors is they're solid phase. And so these ions are traveling through a solid crystal with little to no resistance. I should say little resistance. So their conductivities can easily be as high as copper or even exceed copper. Copper is like the standard for electrical conductivity. It's an excellent conductor of electricity, like gold. Mm-hmm.
What did you say about ionic conductors since they have like charge?
Yeah, we have charged ions.
So how does that help the electrons?
They don't. There's no electrons involved here. Rather than having electrons transport the negative charge from the negative terminal to the positive terminal, we have ions transport the charge. And so it's electricity, but it's not electricity with electrons. It's electricity with ions. So maybe we should call it ionicity rather than electricity because there are no electrons involved. All right. Unfortunately, we don't have any distilled water. How do you distill water? Do you guys remember how to distill water? You boil it. If you take organic chemistry, you can set up something like this. apparatus. Like this. And then we put it in here, we boil it, and any impurities are either left behind or boil off first. The more volatile impurities will boil off first, so you can capture those and then remove them, and then capture the water. There's a thermometer in here, so we know when water is coming out because the temperature will go up to 100 degrees. When we get to 100 degrees, then we're going to collect it. So we'll collect the water here. The less volatile components will remain in this. This is a round bottom flask. So don't break these. These are quite expensive. So we don't have distilled water. Distilled water is expensive. It's expensive because it costs a lot of energy to boil the water. Instead, we use deionized water. How does deionized water purify water? Yeah, we kind of filter it, but these filters capture ions. They're called ion exchange columns. And it's essentially the resin that's in there grabs the ions out of there. So it's kind of like filtering. And so we have our deionized water, which is less expensive, but still expensive for us. And so we try to just use the deionized for chemistry, but for washing, we try to use the tap water and give it a final rinse with deionized water. So we don't really wash with deionized water, just a final rinse to wash off any water spots. But did you say this is going to conduct electricity or not? Let's see. Let's make sure that this is working okay. Yeah. Do you see any light? Let me turn off the light and see. Maybe it's just faint. Do you see any light? No. So what would we categorize water as? Water would be categorized as a insulator, non-conductor. And this is pure water because we purify it using ion exchange columns or deionization process. Not distillation, but it's all right. So why didn't it conduct? Conductivity is about 0. Why is that? Mm-hmm.
I just have a question. It's not really about conductivity. So if like water isn't a conductor, why is it that like if you throw a hairdryer into like that's plugged into a tub full of water, is it because like the electricity or like the electrical systems within the hairdryer that makes it like kind of whatever? It's like if some.
Do you take a bath in distilled water? If you do, you're pretty well off, I'd say.
No.
This would be kind of expensive.
I just feel like typically like in media you'll see like somebody trying to murder somebody else.
Yeah.
Like a hairdryer into the water and they get electrocuted. Is it the body?
No. It's because there's impurities in the water that conduct the electricity. But if it's distilled water and there's nothing leaching into it,
Oh, that's why it was distilled water. I'm sorry. I was just
or deionized water.
yeah.
Yeah, if you're taking a bath with distilled water or deionized water, it's a pretty expensive bath.
Yeah.
Especially with distilled water. What is it, like $1 a gallon? How much is distilled water now? I think it's more than $1. I think I paid $2 last time I got a gallon of distilled water.
So you would do it with regular
It'd be
water?
very expensive bath.
So if you would do it with like regular water that isn't distilled or deionized, would it come down to the same?
We'll see. Let's take a look. But let's go back to pure water. Does pure water have mobility? Can water molecules translate? Yes. They have good mobility. Are there lots of water molecules? You know, a mole of water is 18 milliliters. There's a huge number. Lots. What's missing? Do water molecules have a charge?
Well, did they have like a slightly negative charge?
Okay, they have a slightly negative and a slightly positive. Can the slightly negative part of the water go to the positive electrode, and the slightly in other words, can the water split apart and half of the water go to one side and the other half go to the other side? No. And so water is kind of stuck. It's going to have zero net charge. So if it has zero net charge, what's the electrical conductivity that's expected? Zero. There's no charge. We need charge. And so water is what we call a non-conductor or an insulator. How about tap water? We would expect tap water to conduct, which is these. So let's take a look at some tap water next. Does tap water taste salty to you? Does it taste salty? Not really, but do you know there are salts dissolved in tap water? We call them minerals. Let me turn off the lights so we can see this better. But tap water, will it conduct? Yes. And so this is why you don't want to drop your hairdryer in the bath or the sink, because tap water will conduct. Whereas this is, I don't know, this must be tap water too. Whereas DI water, let me rinse this tap water off. I'm going to rinse the tap water off using DI water. Because tap water has dissolved salts in there, or dissolved compounds. Salts are ionic compounds that aren't acids. You know, so we pretty much call all ionic compounds that aren't acids salts. I don't know what we can try to analyze our tap water to figure out what minerals there are, but for sure there's probably sodium ions in there. Aqueous means what? Dissolved in water or solution. And we're going to have dissolved sodium ions and dissolved chloride ions, and those can conduct electricity, etc. There could be other ones in there as well. And so if I put my electrodes in here, one of them has an excess of electrons, the other one has a lack or dearth of electrons. Then what we're going to see is we're going to see the sodium ions are going to be attracted to which electrode? The negative one. And the chloride ions are going to be attracted to which electrode? The positive one. And that's going to result in electrical conductivity. Electrical conductivity is we have good mobility. These ions can translate. We have enough of them. Although it's not that salty. What do you think would happen if I put seawater or ocean water here? Would it light up brighter? Yeah, for sure. A lot brighter. Because the number will be a lot larger. And these ions have charge, so there's no problem with that. And therefore, we get decent electrical conductivity. So tap water has moderate electrical conductivity. Not as good as this iron metal, but okay. How about solid sodium chloride? So normally I rinse with tap water and give it a final rinse with DI water. This tap water has impurities in it. I don't know what those impurities are necessarily, so we get rid of those impurities at the end and try this on. Solid sodium chloride, should it conduct? Sodium chloride is just table salt. Yes? Solid. No? We'll just check it. Let's see. Do you see any light? No. The electrodes are still a little wet. Let me just make sure this is still on. Yeah, it's still on. But it didn't light up, did it? Okay, so let's take a look at solid sodium chloride next. Why not? I'm sorry? Well, what does sodium chloride consist of? Sodium and what's the charge on sodium? Plus. And the charge on chlorine? But wouldn't they have canceled out in tap water? We have a plus and a negative. Shouldn't they have canceled out there? So shouldn't it have been a non-conductor? In water, the negative and positive are what we call partial, and they're stuck on the same water molecule. You're right, this cancels out like this, but the sodium is free to move one way, and the chlorides can be free to move the other way, can it? Or do we take the whole thing? And so when you visualize the structure of sodium chloride, what does it look like to you? Sodium chloride would be, a lattice. And when we look at a lattice's structure is going to just consist of sodium and chlorides. Sodiums are smaller, chlorides are bigger. So we have lots of sodium ions and lots of chloride ions, and those all have charge. So we do have charge. Do we have a large number of ions? Yes. Do we have mobility? No. There's no mobility. Because in a lattice of sodium chloride, the only motion we have is what type of motion? Vibrational. And so all we're going to have here is vibrational motion. No translational. We need translational motion. Zero translational motion. If there's zero translational motion, there's no conductivity. And so we call this an ionic lattice structure, or a crystal lattice, or an ionic crystal lattice. How can I free up the ions? And so let's take a look at what we're doing next. The next one we're doing is NaClAq. So let's take a look at that. I'm going to start from solid sodium chloride. So when I think about sodium chloride solid, I think of a crystal lattice like this. In which we'll just have vibrational motion. And then the first step in this is something called solubility. That is, will it dissolve in water? Does sodium chloride dissolve in water? Yeah. It turns out that sodium chloride is quite soluble in water. If I have 100 milliliters of water, I can dissolve 36 grams of it, which is quite a lot. If I try to dissolve 37, then 1 gram will remain undissolved, be saturated. But it's still quite soluble. The next step of this, we look at something called electrolyte properties. For electrolyte properties, we have 3 categories. We have strong. Strong means when it dissolves, it dissociates into ions. And it dissociates close to 100% into ions. So sodium chloride we call a strong electrolyte. The reason we call it a strong electrolyte is because when it dissolves, it dissociates into sodium ions and chloride ions near 100%. We also have weak electrolytes. Weak electrolytes partially dissociate. And third, we have non-electrolytes. Non-electrolytes do not dissociate into ions. So an example of a non-electrolyte would be water. Water doesn't conduct electricity because it won't dissociate into ions. It stays together as a neutral water molecule. Whereas sodium chloride, Whereas sodium chloride, we predict it should conduct electricity because it's a strong electrolyte, and strong electrolytes dissociate into ion when dissolved in water. And so what happens here is, one, solubility, the water molecules come here and tug at the ions. it turns out that the oxygen end likes to attack the sodiums, and the hydrogen ends like to attack the chlorides. And if they're collisions, which they're going to be because the waters have translational motion, they're collisions, these can knock the ions off or pull them off, or a combination of knocking them, pulling them off. When that happens, we're going to have what we call the hydrated ions. And so let's say the sodium ion breaks off. What's going to happen is it's now going to be surrounded by water molecules. The water molecules are going to help stabilize the charge, because when we have an imbalance of charge, we'll have static electricity is generated, which can result in a shock. And so having a bunch of water molecules surrounding this will help stabilize it. And so this is called a hydrated or solvated ion. And water is good at doing that because the hydrogens can go towards positive ions and the oxygens can orient towards negative ions. So the oxygen end would be pointed towards the let me fix this. The negatives. I'll just be consistent with my drawing here. Let me change this. So up here we have a hydrated sodium ion, down here we have a hydrated chloride ion, and these have translational mobility. And so the ions can move in the water. And that's what we want for this. And so what I'm going to do is I'm going to use some deionized water here. I don't want to use tap water because I want to make sure that what we're seeing, if there's any conductivity here, is due to the salt water. And so let me make a little salt water here, and let's see what happens to the light bulb. You see that? Now this is really salty. A lot saltier than tap water. This is what we call saturated because you see I have more sodium chloride than will dissolve in here. If I look at tap water, I have a lot less sodium chloride in here than will dissolve. So the tap water is not so bright. But this saturated sodium chloride is really bright. And so that tells you there are a lot more charge carriers here. So strong electrolytes should conduct electricity pretty well, right? However, there are two ways we define electrolyte properties. One way is by electrical conductivity. So if it has strong electrical conductivity, we call it a strong electrolyte. The other way we define electrolyte is by dissociation. If it dissociates 100% into ions, we call it a strong electrolyte. So did solid sodium chloride have much conductivity? No, it had zero conductivity. Should we still call it a strong electrolyte? Well, it depends. When sodium chloride dissolves in water, yes. And therefore, we could call sodium chloride a good electrolyte. But in terms of electrical conductivity, did solid sodium chloride conduct much electricity? No. And therefore, we shouldn't call it a good electrolyte. We should call it a poor or non-electrolyte. And so is sodium chloride a non-electrolyte, or is sodium chloride a good electrolyte? Or a strong electrolyte? And that results in confusion because there are two definitions for electrolyte. If you're a battery person, battery people are really interested in electrolytes, then all you care about is electrical conductivity. And so if it has good electrical conductivity, you call it strong. If it doesn't have any electrical conductivity, you call it a non. But for us, we're going to define it based on how much dissociates. If all of it dissociates, then we're going to call it strong. But that doesn't mean it's going to have good electrical conductivity. Because, this is saturated. But what I could do is I can take some of my saturated sodium chloride here and then dilute it. I'm going to dilute it with DI water. So this is what we call unsaturated, and it doesn't have that much sodium chloride. Is this going to conduct electricity as good as the saturated sodium chloride? Well, it kind of looks like it, right? It's pretty good. But what I need to do is I'm going to dilute it even further. This is called solution dilution. Just add water. Just keep adding water. Okay, let's test it now. Is it getting weaker? I'm going to dilute it more. How about now? Can you see it? Yeah, you can barely see. Do you see the red glow on there? It's barely there. So should we still call sodium chloride aqueous a strong electrolyte, even though this is sodium chloride aqueous, but look how dim the bulb is. I mean, you can barely see it, right? And so should we still call it a strong electrolyte? Versus, this is saturated sodium chloride. So should I call this sodium chloride weak and this sodium chloride strong, or should I just call sodium chloride strong? What should I do? What we need to do is we need to just use one definition probably rather than two. If I was working with batteries, this would for sure be weak. This would be strong. But it's the same stuff. It's just different concentrations. And so what we're going to do is we're just going to call sodium chloride a strong electrolyte because it dissociates. Whether it's a great conductor or not just depends on its concentration. Does that make sense? Because we're going to say if it splits up 100% into ions, it's a strong electrolyte. Now solid doesn't split up because there's nothing pulling it apart. So for solid sodium chloride, it's a bit ambiguous what you want to call it. It's a bit ambiguous because you could call solid sodium chloride a strong electrolyte because hypothetically, if you did dissolve it in water, would it split up? Yes, it would split up. So don't get too hung up on the definition of electrolyte because people will define it differently depending on who you talk to. This process of dissolving is called dissolution. And when we dissolve something, it could result in three possible scenarios. When we dissolve something, one, a little bit has to dissolve or a lot has to dissolve. That's solubility. Two, what it's going to do when it dissolves is either dissociate, partially dissociate, or not dissociate. And so we look at these three categories here. So sodium chloride is soluble, but what happens when it dissolves? Well, what happens when it dissolves is it dissociates. Therefore, it's strong, regardless of how well or how poorly it conducts electricity. We can use some quantum mechanics to simulate this. So this is called molecular dynamics, and it's just using quantum mechanics to take a look. Let's watch this. So there's a small crystal of sodium chloride. You can see its lattice structure, just alternating. The sodiums are these dark ones, the chlorides are the green ones here. There's some temperature here, so there's some vibration. They just have this sitting in some water here. You can't see the water molecules. They're moving very fast. So this is surrounded by water molecules here. The water molecules are going to be tugging and pulling apart. And so now we have hydrated ions. Do you see those? Eventually the whole thing dissolved. And so this has got to be less than 36 grams per 100 milliliters worth of sodium chloride, since all of it dissolved, resulting in an unsaturated solution or maybe a saturated solution. We could try throwing some more solid sodium chloride in there to see if more will dissolve or not. Here's another molecular dynamics simulation, except this molecular dynamics simulation is a lot slower. Do you see that? And so here we see the water trying to pull on the chloride ion, the gold one. The sodiums are the blue. This one they have synced to some music. This is you think something's going to happen, but nothing's happened. You might have to wait for the next movement. This is extremely slow, so let me fast forward it. We still haven't gotten one ion to break off. You know what this reminds me of? Sodium chloride is what we call soluble, but this one just really doesn't want to dissolve. If you have a salt that really doesn't want to dissolve, do you know what we call that? Insoluble. So this is looking like an insoluble salt rather than a soluble salt. Now what's preventing the insoluble salt from dissolving? What's preventing it from dissolving are these electrical attractions. The electrical attractions between the positive and the negative are too strong. And so water comes here and it tries to break off these ions, but what we call the ionic bond, that is the electrostatic attraction between the positive and negative ion, is just too strong. You know, how long have these waters been trying to pull off these ions? There we have one successful. But how long would it take for the salt to dissolve? It'll take a long time. So let's see. So even though that was labeled sodium chloride, that was in super slow motion. Even the first one that we saw was in slow motion. First one happened pretty rapidly, but they slowed it down so you could kind of see the movement or the motion of the water molecules and the lattice, the crystal lattice. All right, what's next? 2:30, 3:30. All right, well, we'll take a break here next. So let me pause this. PbI2 solid is a molecular or ionic compound? Ionic. What's the name of this? We would name it lead diiodide if it were a molecular compound, because it would be a binary molecular compound. But since it's an ionic compound, we don't name it lead diiodide. We would name it lead 2 diiodide, or just iodide? Just iodide. And the reason is because of ionic compounds, we can figure out the ratio. So if it's a lead 2 ion, then we're going to need 2 iodides in order to balance out the charge here. And so the ratio can be determined by the charges on the ions. Therefore, we don't need the prefix. Like, for example, carbon can have CO and CO2. Here, these are binary molecular compounds, and we don't know which carbon that is. And therefore, we have to say carbon monoxide or carbon dioxide. We can name these as ionic compounds if we write the charge on the carbon. So this is carbon 2 oxide. This would be carbon 4 oxide. But traditionally for binary molecular compounds, we only use the prefixes. We don't use the charges. So I don't state what the charge on carbon is. There's a reason for that. And then for ionic compounds, we use the charges to figure out the ratio. So this is just lead 2 iodide. And it's a solid. And so what type of structure? Does it form molecules or ionic lattice? It forms an ionic lattice, but the ionic lattice is not going to be the exact same because of the ratio. You know, I have 2 iodides for every lead. And so, but I'm going to kind of draw it the same here. And so we have an ionic lattice like this. Now, is this ionic lattice going to conduct electricity? So lead 2 is more hazardous. Somewhere this. Lead forms a lot of colorful compounds like this. They use a lot of lead compounds in paint pigments. So this is a really nice orange. Lead also forms a really nice white. You know, a very bright white color on that. And it's also a heavy metal, so I don't want to touch it. You know, and it's a powder, so I don't want to sneeze here. If I sneeze here, I'll just create a dust cloud of lead 2 iodide, which I don't want. Lead 2 is much more common than lead 4, so if you just see lead iodide, it's most likely lead 2. So they didn't name this properly. It should be lead 2 iodide. Will it conduct electricity? Yes? Solid lead 2 iodide. Let's take a look. Oh, I don't have it plugged in. Plug it in. Let's see if it conducts. Does it conduct electricity? No. Even if I turned off the lights. It doesn't. Why? The charge is there. The lead ions are +2. The iodide ions are -1. And so we have charge. What are we missing? Yeah, in solids, what type of motion do we have in solids? Vibrational. Since there's only vibrational, in order to conduct electricity, we need translational motion. Yeah. And so the problem is not the number. Z and N are okay. Mu is no good. And therefore sigma is no good. No mobility. No mobility, no conduction. So what we can do is we can try to break apart the lattice using water. And so this is a solution of what we call saturated lead-2 iodide. Saturated lead-2 iodide is just dissolving as much lead as possible in this. And so we can see some excess lead-2 iodide on the bottom that doesn't dissolve. And so the maximum amount here. And for this, I'd like to wear gloves, but I don't have them, so I'll just be careful handling this. Lead is a heavy metal and leads to heavy metal poisoning. And heavy metals like sulfur and sulfur protein, so it could screw up some of the functions proteins. But let's see if this conducts electricity. Do you see that? It conducts. Is it very bright? It's not very bright. Since it's not very bright, should we call it a weak electrolyte? Since it's not very bright? I'm just going to use some of this to wash that. There. We have to watch out for cross-contamination. And so I have a waste beaker here. I'm going to just rinse off the electrodes so I don't get the lead in what I'm going to measure next. And then I got to watch out because if I handle lead, then if I rub my eyes or eat a sandwich or something, I can cross-contaminate myself. So proper chem hygiene requires washing hands afterwards. This is what happened with the NASA astrobiologists, they think. What happened was, you remember Mono Lake, the NASA astrobiologist? They're thinking that the bacteria, the source of the arsenic was cross-contamination, not the bacteria itself. Why wasn't it, okay, so why wasn't it very bright? Well, it wasn't very bright because it didn't conduct much electricity, but that was saturated. So this is PbI2 aqueous saturated. Saturated is either SAT or SATD. And what saturated solution means is I have the maximum of lead, maximum amount of lead-2 iodide that will dissolve in that amount of water that's saturated. So for example, a saturated salt solution would have 36 grams of sodium chloride in 100 milliliters of water. In this case, the saturated solution of this is like the second video we watched. The second video we watched, the water molecules really struggled to remove the ions in that second video. And so what we have is, if we take PbI2 solid, like this, and we dissolve it in water, it has very limited solubility. So most of the solid stays as solid, like this, and very little actually dissolves. And so we say that this is low or limited solubility. But whatever did dissolve, we're going to form hydrated ions. And so if this is an iodide, then the oxygens will be pointed towards the iodide. And we'll end up with hydrated ions. And if this were a lead here, the hydrogens on water would be oriented towards that. And so it's just the water really struggled to break apart the lattice here. And as far as electrolyte properties go, would we call it a strong electrolyte, weak electrolyte, or non-electrolyte? If we're basing it on electrical conductivity, how bright the light bulb is, then we call it weak. But we're not. We're going to use the other definition. The other definition is whatever dissolves dissociates into ions. And so even though not much of the lead dissolved, whatever lead did dissolve dissociated in the ions. It was just very dilute. And so what we have here is this. What we'd say is that PbI2 is a strong electrolyte because whatever did dissolve dissociated, but has limited solubility. Limited solubility means N is small. A strong electrolyte means that we have Z and we have mu. But just N is small, the number. And therefore the conductivity is small. Uh-huh.
Could you say that also about the sodium chloride one? That technically the electrolyte is strong, but because of, I don't know. It depends on how dissolved it is.
Sort of. For lead, it's limited solubility. For the sodium chloride, it was because of dilution. I made it overly dilute, or I didn't add very much sodium chloride. But sodium chloride has high solubility. It has high solubility. You can see how bright the light bulb was in a saturated solution. But if I make it highly unsaturated, it's going to get dimmer and dimmer and dimmer. You know? But this was the best I could do with lead. I couldn't get it any brighter than this.
But it's still a strong electrolyte.
Yes. It's a strong electrolyte not because it conducts a lot of electricity. It's a strong electrolyte because it dissociates. What does dissolve dissociates into ions. So we need to talk about solubility. And so the lead is like the second video. In the second video, barely any of the ions got dissociated, even though that second video was sodium chloride. That was behaving like lead. The first video is behaving more like sodium chloride. And so we're going to look more in depth on solubility, and we're going to come up with a set of rules for these. The rules we look in terms of molecular compounds and ionic compounds. So the solubility rules for molecular compounds are pretty straightforward. This is one. It's called like dissolves like. And so an example would be oil and water. There are certain structural features in oil and water that are quite different. And so oil and water are what we call insoluble in one another. But we could have something like ethanol. Ethanol and water have certain structural features that are very much alike. And since they're very much alike, they're soluble. The same thing with sugar. When you think of sugar, sugar and water don't seem very similar at all, but when you look at it structurally, they have certain characteristics that are very similar. and therefore they're soluble. We'll look at these structural characteristics later, but basically the solubility rule here is simple to remember. Like dissolves like. For ionic compounds, the solubility rules are a bit more involved. For ionic compounds, first we look at the cation. Cation comes first, and it's a positively charged ion. In fact, they named these pieces of copper here electrodes, and then they further named the electrodes depending on the direction or the charge on them. And so we have electrodes named cathode. The electrode that's named cathode, the cations go to. And there's an electrode named the anode, and that's where the anions go to. Well, when we look at the solubility of ionic compounds, first we look at the cation. And so that gives us rule 1. If the cation is a group 1 being hydrogen, lithium, sodium, etc., and ammonium, these are all soluble, regardless of the anion. And so an example of this would be ammonium phosphate. Do you know the formula for ammonium phosphate? Well, ammonium is NH4 plus. What is phosphate? PO4. Charge? -2? No, not -2. Okay, look at the position of phosphate and tell me what its charge is. It's -3. Yeah. All right, so what's the correct ratio of ammoniums to phosphates? I could use the simple cross multiplication rule. How many ammoniums? 3. How many phosphates? 1. So if I'm looking at solid ammonium phosphate, is that soluble or insoluble? Well, they're all soluble, so we'd say it's soluble. I'm going to use S for soluble. We have 3 categories of solubility. S is equal to soluble. And the cutoff here is we want greater than 0.1 moles to dissolve in a liter. So if we can get more than 0.1 moles of that salt or the ionic compound to dissolve, we're good. Salt and ionic compound are the same, basically, except for acids, which begin with H. We have SS. SS stands for slightly soluble. Slightly soluble is about 0.1 moles will dissolve in a liter. And then we have insoluble. Insoluble is less than 0.1 mole will dissolve in a liter. And so ammonium phosphate is soluble. Well, what if it isn't one of these cations? Then we look at the anion. And so we go to number 2 here, and we look at nitrates.
So if you're looking at that compound and you see like there's a cation, you see the cation first, and if it's group 1 or ammonium, then it's automatically soluble?
Yes,
Okay.
regardless of the anion. So it could be sodium sulfide, sodium sulfate, sodium sulfite, sodium phosphate, sodium whatever. They're all soluble. If it's not one of these cations, then it's easier to look at the anion. And so the anions that we look at first are nitrate. What's the formula for nitrate? Charge? Nitrate acetate. Formula for acetate? Charge? -1. Good. Chlorates. Charge? Negative. So nitrates, acetates, chlorates, it doesn't matter what the cation is. These are all soluble. So if I look at this, what is the formula for lead-2 nitrate? How many NO3s do I need? Is it soluble? Yes? Yeah. All nitrate salts are soluble. It doesn't matter what the cation is. Blank, blank nitrate, blank nitrate, they're all soluble. Same thing with acetates and chlorates. These are rules. There are exceptions to the rules, which we aren't going to talk about yet. 3. If it's not one of these, then we look at chlorides. What's the formula for chloride? Charge? Bromide? And iodides. These are all soluble, except, now we have some exceptions, except when paired with silver ions, lead-2 ions, and mercury 1. What's the formula for mercury 1? Yeah, Hg2 2+. So we go to lead-2 iodide, which we just looked at, PbI2. PbI2 we would say is soluble, insoluble. Well, they're all soluble except for lead-2, so this is insoluble. It's one of the exceptions. How about mercury 1 acetate? What's the formula for mercury 1 acetate? This one doesn't fall in the chloride, bromine, and iodide, but it does fall in the acetate. And so this would be nitrates, acetates, and chlorates are all soluble. So we'd say soluble here. How about iron 3 chloride? What's the formula for iron 3 chloride? FeCl3. Is that soluble or insoluble? This is soluble. All right. After chlorides, bromides, and iodides, we look at sulfates. What's the formula for sulfate? SO4 charge. SO4 2 minus. Are all soluble except when paired with silver, lead 2, mercury 1, mercury 2. What's the formula for mercury 2? Hg2 plus. Calcium, what's the formula for calcium ion? Charge? Yeah. Strontium, charge? Same, this is in the same family. Barium, 2 plus. How about this? What do you name this? BaSO4. Barium sulfate. Is it soluble or insoluble? Insoluble. How about this? MnSO4. What do you name that? Manganese sulfate? Close. Not manganese sulfate. Manganese. What are the common charges of manganese? Look where it's located on the periodic table and tell me the common charges of manganese. So which one is it? The +3 or the +2? And so we have to designate which one it is. Otherwise we have to use the rules for binary molecular compounds. If we don't tell what the charge is, then we don't know how many sulfates are on there. And so we need to know this. It's got to be a manganese 2 sulfate. Whereas barium, why didn't we have to do the same thing with barium? Yeah, it only has one charge. Tell me what the formula for manganese 3 sulfate is. And so the way I do it is I do 3 here, and then sulfate is 2 minus. And then there are 2 ways you could do it. You could just list the ions out until they balance, or you could do the cross. We'll do the cross. So how many manganeses do I want? I want 2 manganese. So it's going to be Mn2. And how many sulfates do I want? 3. So it would be Mn2SO43. Is this soluble or insoluble? Soluble. How about manganese 2 sulfate? Soluble or insoluble? This is also soluble. Here. All right, that's number 4. Now, those were mostly soluble. In number 5, these are going to be mostly insoluble. And so the first one we're going to look at is hydroxide, OH minus. Hydroxide salts are insoluble, except when paired with silver, lead 2, mercury. Oops, what am I doing? Sorry. Let me backtrack. Sorry, I need to erase this. These are all insoluble. I have to do the soluble exceptions. And so now I got to switch my thinking. These are insoluble except when paired with group 1 and ammonium and calcium, strontium, and barium. Name this. Magnesium 2 hydroxide. Would you agree? Magnesium 2 hydroxide?
Is that like CFR?
Which one?
Like the first one, so you know how you have ammonium? What is the one that's on the left?
Calcium. Ca.
The other one.
This one?
No, not sodium. No, the first one. The first one.
This one?
Yeah.
Group 1.
Oh.
Group 1 would be the alkali metals, including H+. All right, what are the common charges for magnesium? Element number 12. Is it fixed charge or variable charge? It's fixed charge. If it's fixed charge, we don't have to write a Roman numeral. If we don't need a Roman numeral, we just call it magnesium, because we're not going to get it mixed up. There's only one charge for magnesium, and this would be called magnesium hydroxide. Is magnesium hydroxide soluble or insoluble? Insoluble.
Wait, I thought we were doing the hydroxide was insoluble except in these groups, and magnesium is part of like the same group as calcium, sodium, and barium.
It is, but it's an exception. Let's do this one. What is this called? Calcium or calcium 2 hydroxide? Calcium hydroxide. Is it soluble or insoluble? It's soluble. So magnesium was purposely left out because it's insoluble, whereas calcium hydroxide is soluble.
It's everything but magnesium.
Yeah. How about this one? Sodium hydroxide. Is sodium hydroxide soluble or insoluble? Soluble, it dissolves in water quite easily. You could buy sodium hydroxide in the supermarket. Have you seen it? You could buy solid sodium hydroxide in the supermarket. It's called lye or drain cleaner. And so you take the chips or chunks of sodium hydroxide and you put it down your drain. And the hydroxide, the sodium doesn't really do anything. It's the hydroxide. The hydroxide will dissolve fats and hair, whatever else. It reacts with it chemically. This is lye or drain cleaner. Sodium hydroxide, drain cleaner, is poisonous. Do you know you could buy magnesium hydroxide in the supermarket too? Do you know what magnesium hydroxide is called? It's called milk of magnesia. It's kind of this pink, milky suspension. The magnesium hydroxide doesn't dissolve very well, and so it's like this pasty, semi-solid. Have you ever seen it? Very pasty. Milk of magnesia is not in the drain cleaning section. So let's say you went, your sink is clogged, you went to the supermarket to buy some drain cleaner and they're all out. And then you went down the aisles and checked all the ingredients. And then you came across milk of magnesia, which is magnesium hydroxide. And you go, wow, magnesium hydroxide, that has even more hydroxide than sodium hydroxide. If you look at magnesium hydroxide, how many hydroxides are there? There are 2 hydroxides for every 1 magnesium. So that might be even better drain cleaner, twice as powerful. Would you think it's twice as powerful? Yeah? You got twice as much hydroxide. Maybe it's twice as powerful.
Is it the hydroxide?
It's the hydroxide that does it. Sodium, doesn't really do anything. Magnesium doesn't really do much either. It's the hydroxide. So if the supermarket ran out of lye or sodium hydroxide, could you use milk of magnesia instead? You could, but is it going to be very effective? Why not? Or
Why wouldn't it be as effective as what's important? It's the hydroxide.
it isn't. It isn't as effective, and so what can you think might lead to it being less effective than sodium hydroxide? It's insoluble. It doesn't really dissolve. What we have to have is we have to free up the hydroxide so that they can attack the fats that are clogging the sink or the hair that's clogging the sink or whatever is clogging the sink. And if it's not very soluble, where are the hydroxides? Is this an ionic compound or a molecular compound? It's an ionic compound. The hydroxides are locked in the crystal lattice. And so it's not going to be as effective because there isn't as much hydroxide free to react. That's why. Likewise, let's say you went to the supermarket to buy milk of magnesia. Do you know what milk of magnesia is used for? Yeah, it's used for constipation. It's laxative. If you went to go buy some milk of magnesia and they were out of milk of magnesia, could you instead use drain cleaner for anti-laxative? No? Why not? Because it's half as powerful. Isn't it half as powerful? It only has 1 hydroxide versus milk of magnesia, which has 2 hydroxides. So shouldn't 2 hydroxides be more powerful than 1 hydroxide? Or am I thinking about it wrong? I'm thinking about it wrong. I wouldn't use sodium hydroxide because it's pretty deadly stuff.
What does it do
how this works as a laxative, I don't know. It would work as an acid, though, that's for sure. Because we call these bases. Bases are often used in soaps and cleaners and whatever else. But you wouldn't. And it's not because of how many hydroxides there are per formula unit. It's because of the solubility. That's why. So what we say is that sodium hydroxide is very reactive. However, magnesium hydroxide isn't so reactive. It isn't so reactive because the ions are kind of locked in a lattice. And so the next compound here, you know, I've had milk of magnesia, and I've had this compound. I've had this next one, which is called what? Barium sulfate. Do you know when I had this? I had to drink a cocktail of barium sulfate for CAT scan as an imaging agent. And so it's like milk of magnesia. It forms like this chalky, pasty suspension. And it doesn't taste bad. But what it is barium is what we call a heavy metal. The heavy metals are near the bottom of the periodic table. So barium and lead are both heavy metals. And one characteristic of the heavy metals is they have a lot of electrons. And things with a lot of electrons are good at absorbing X-rays. And so rather than having a lead cocktail, I had a barium cocktail. I much prefer a barium cocktail over a lead cocktail. And then what they do with that is then they can image it because barium absorbs X-rays very nicely. And so the barium sulfate, but the barium is a heavy metal, but fortunately it didn't kill me because is barium sulfate very soluble? No. Barium sulfate is insoluble. It's one of the exceptions. And so even in stomach acid, it's not very soluble. So I didn't get much barium into my blood stream. And so I was fine. The next CAT scan I had was with iodine. Iodine also has a lot of electrons, but it's not a heavy metal. But I had an allergic reaction, a mild one, to the iodine. So that was it. So if I had barium nitrate cocktail, then that would be pretty poisonous, right? Versus the barium sulfate. As barium sulfate's insoluble, barium nitrate's soluble, and I wouldn't have wanted. So if they ran out of barium sulfate, I wouldn't have wanted a barium nitrate cocktail, or a barium acetate cocktail, or a barium chlorate cocktail. All right, let's go on to 6. That was hydroxides. And now we're going to go to sulfides. What's the formula for sulfide? With a D? S2 minus. These are all insoluble. Except group 1, ammonium, and group 2. Roman numeral 2 or the number 2 is fine. And so let's take a look at this. What is this called? Manganese. Manganese sulfide or manganese 2 sulfide? Manganese 2 sulfide. What is this called? Magnesium or magnesium 2? Just magnesium or magnesium 2? And it's just magnesium. Is magnesium sulfide soluble or insoluble? Is manganese 2 sulfide soluble or insoluble? Insoluble. Okay, so those are some examples of sulfides. And then the last rule we have Or for carbonates, what's the formula for carbonate? CO3, 2 minus. Chromate, charge. Phosphate, carbonates, chromates, and phosphates are all insoluble. Except group 1 and ammonium. And so let's take a look at phosphate. Let's look at calcium phosphate. What's the formula for calcium phosphate? Soluble or insoluble? Insoluble. What's the formula for potassium phosphate? Soluble or insoluble? Okay. So those are some solubility rules here. And let's do a little thing on heavy metals. You know, there are some homes that use lead pipes, and the lead can get leached into the drinking water. Some of the older homes. And then lead used to be a common pigment in paint, like especially white paint. Lead oxide has got this really intense white color. And so what can result is heavy metal poisoning. I didn't get much heavy metal poisoning from the barium cocktail because it wasn't very soluble, so I didn't get much barium in my blood. But some people do get a lot of poisoning, but there's a treatment for that. And there are two drugs that used to be used, but both drugs relied on EDTA. EDTA is kind of a big anion, and it has a 4- charge. It's called ethylene diamine tetraacetate, and it's just abbreviated, or tetraacetate. It's abbreviated EDTA, 4-. And there are two versions of EDTA. There is sodium EDTA, and there's calcium EDTA. Which one do you think is a more aggressive drug? Sodium EDTA or calcium EDTA?
Calcium.
How come calcium? Or let me tell you, which do you think is more aggressive for drain cleaner? Sodium hydroxide or magnesium hydroxide? Which one would be a more aggressive drain cleaner? Because drain cleaner, we need hydroxide. Which one would be more aggressive, sodium hydroxide or magnesium hydroxide? You'd say magnesium. Oh, so milk of magnesia would be better than lye
No.
for drain cleaning?
Well, you said it was because magnesium is not soluble. It's insoluble.
In other words, if you're going to clean your drains, are you going to pour laxative, anti-laxative in there? Or are you going to pour drain cleaner in there? And why, can you drink drain cleaner? Can you drink milk of magnesia? Why? It's not soluble. It's not as aggressive. It's not going to kill you because having too much hydroxide is going to cause a lot of trouble. Let's see if I lost that. So in the treatment of heavy metal poisoning, we need EDTA. Which one is going to be more aggressive, sodium EDTA or calcium EDTA? Sodium EDTA is more aggressive, much more aggressive. It's like, okay, if you're going to grab a bottle of EDTA, in other words, if you're going to grab a bottle of drain cleaner, you have two choices of drain cleaner, sodium or magnesium hydroxide. Which one will you grab? The sodium, if you have to be aggressive with your clogged drain. Does that make sense? All right, and so both of these options are available at the hospital. So let me just finish with this. This is called chelation therapy. So chelating agents bind to lead. And, lead poisoning is a problem. And there's calcium EDTA, and there's sodium EDTA. For sodium EDTA, hospital pharmacies should evaluate them if it's necessary, because sodium EDTA, let me try to fix this so we can... is more aggressive, and therefore sodium EDTA is not administered to children. Sodium EDTA is for acute cases of lead poisoning where the lead level is way too high. You need to bring it down aggressively, otherwise it's going to cause problems, and it's just for adults. So the use of sodium EDTA, the use of sodium EDTA is recommended only when the severity of the clinical conditions justifies the aggressive measures associated with sodium EDTA therapy. According to the package insert, sodium EDTA is indicated in selected patients for the emergency treatment. So let's take a look at some case reports. In Texas, in February 2005, a girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary blood lead level, BLL, of 47 micrograms per deciliter. A venous BLL of 48 micrograms per deciliter obtained 12 days later confirmed the elevated blood lead levels. A complete blood count and iron study conducted concurrently revealed low serum iron levels and borderline anemia. So on February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. And chelation therapies with EDTA. The patient's blood electrolytes at admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral Sexamer, an agent primarily used for the treatment of lead poisoning. The medication order was subsequently corrected by the pediatric resident to intravenous calcium EDTA. So they accidentally specified the drain cleaner stuff rather than the more mild stuff here. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. And so the levels were normal. At 4:35, she was administered 200 milligrams of oral Similar. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA, the drain cleaner stuff, instead of the calcium EDTA, was administered. An hour later, the patient's serum calcium had decreased to 5.2 milligrams per deciliter. Normal value is 8.5 to 10.5. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. That's at 7:05. At 7:25, a cardiac resuscitation code was called. And then at 7:55, and they continuing to resuscitate. And then at 8:12 a.m., she was pronounced dead. Can you believe that? Just by grabbing the bottle of drain cleaner rather than grabbing the bottle of milk of magnesia. Well, anyway, that's not the only case. 2005, a 5-year-old died. It's again, sodium EDTA rather than calcium EDTA. A 53-year-old died, and etc. And this is the CDC report. So the CDC report are deaths between 2003 and 2005 in Texas, Pennsylvania, and Oregon, associated with mixing up sodium EDTA and calcium EDTA. And so the final recommendation, you know what the final recommendation by the CDC is? The final recommendation is to get rid of sodium EDTA. That way people don't mistake it. Because it sounds the same. Doesn't it sound the same? EDTA, sodium, calcium, what's the difference? Right? Should it make any difference? Sodium hydroxide, magnesium hydroxide, what's the big deal? They're both hydroxides. Well, anyway, are we out of time? What time do we go till today? 5:40? Oh, we have more time. So that's good. Let's continue. So the next thing you want to do is you want to look, are there any patterns in the solubility rules? Do you see any patterns there? So if something were not on this list of rules, could you kind of figure it out? Maybe, if you know the patterns. All right, so the next thing we're looking at is saturated barium sulfate. So this is it here. There's a bunch of white barium sulfate down here. Let's take a look. What do you expect? Barium sulfate, soluble or insoluble? Insoluble. So is there going to be much barium and sulfate ions present? No. Do you see it? Yeah. Barely any. And so what do we say? We're going to say it's a barium sulfate is a strong electrolyte, but limited solubility. It's a strong electrolyte, meaning that what does dissolve breaks apart, but so little of it dissolves because it's an insoluble. Insoluble does not mean 100% insoluble. Insoluble just means less than 0.1. If we wanted to know how much, then we have to look up its solubility, its quantitative solubility. So barium sulfate, is that ionic or molecular? Ionic? And so we expect a lattice type structure. And in this case, water molecules are going to have a hard time breaking apart the lattice. And so not much is going to dissolve. Why does water have an easier time breaking apart some lattices and a harder time breaking apart other lattices? And so this comes out. Do you see one pattern in the solubility rules? One of the patterns that I see in the solubility rules is that the higher the charge, the more soluble or the less soluble the salt is. The more soluble? So what's the highest charged species on the... Well, EDTA is not on our solubility chart. What's the highest charge? Phosphate. The lowest charged ones would be like group 1. So, or chlorides, bromides, iodides. So which are more soluble? Which are less soluble? The higher charged or the lower charged? The lower the charge. And so the higher the charge, remember Coulomb's law? The Coulomb's law stated that the force of attraction is proportional to what? The charges on ion A and B divided by the distance squared. And so the higher the charge, the stronger the force or the weaker the force? The stronger the force. And these lattices are like this. Did I already talk about this? If I'm a sodium, how many chlorides do I want to bond to? If you're a sodium, do you just want to bond to one chloride? And then just make a pair like that? What if another chloride comes along and bonds like this? Is there something that prevents this other chloride from sticking to the sodium like that? Is there? I'm sorry? No, it's a positive. If you're positive charge, you want as much negative charge or as much positive charge around you? If you're positive charge, you want as much negative charge around you. So if a sodium's sitting there, then all these negatives are going to be attracted to that. And how many can you fit around it? So each sodium here is now bonded to how many chlorides? 4. In 3 dimensions, that's in 2 dimensions. In 3 dimensions, we'll have number 5 on top and number 6 on bottom. And so it turns out that each sodium is bonded to 6 chlorides. Well, how can that be? Well, the way that can be is this. Each chloride is bonded to how many sodiums? So if you're a chloride, you want to bond to as many positives as possible. And due to the Coulombic attractions, that's exactly what's going to happen. So we're going to get 4 here in the plane. Actually, these are supposed to be touching. I didn't quite draw it big enough. And then 1 on top and then 1 on bottom. So each chloride is bonded to how many sodiums? 6. So do you see there's no unique sodium chloride molecule? Do you see a sodium chloride molecule in there? No, it's because of the way ions are. If you have a positive, it's going to attract as many negatives as possible. So this is like if you have some food out, and that food, it doesn't just attract one fly, it attracts a whole bunch. If you're on an outdoor picnic and you're trying to get the flies away, it's going to attract as many flies as possible. And so the same thing, a positive attracts as many negatives, and a negative attracts as many positives as will fit around it. And so for sodium chloride, we can fit 6 of the opposite around it, and therefore we build up a lattice like this. Now, what holds the lattice together? What holds the lattice together are Coulombic or electrostatic attractions. And so it's related to the charge and the distance between the center of the charges. And so let's say I built up a lattice, rather than with +1, I built it up with +2. So if I have a +2 here, what are the negatives going to do? The negatives are going to be more strongly attracted to this. In fact, they're going to be attracted. If I made the cation +2 now, and the anions stay at -1, how much stronger is the force? The force is going to be double. If I made the cation +2 and I made the anion -2, how much stronger is the force? Quadruple. And so when water comes along, it's going to have a harder and harder time pulling apart the ions when they're more strongly bonded, according to Coulomb's law. So something like phosphate, the higher charged ions are going to be more insoluble. And so in other words, as Z increases, the solubility decreases. So increasing charge means decreasing solubility. But then you go, why silver? Silver is only +1, and it seems to not be very soluble, but silver is extremely small. That's why. That's one of the reasons why. Whereas some of the other +1 ions are a lot bigger. Ammonium's quite big, and so the size and the distance have something to do with it. And so we need to learn a little bit about the sizes of the ions. So this brings up a question. How come fluoride? When I do this, chloride, bromide, iodide, but what happened to fluoride? The reason fluoride is left off there are there are too many exceptions. So if you want to know the fluoride solubility, look it up on Wikipedia. Or if you want a solid source, Wikipedia is not considered necessarily a trustworthy source. There are other sources that are considered more trustworthy. The other sources would be the CRC handbook of chemistry and physics. And the other one is the Merck index. These are very trustworthy sources because the data is reviewed all the time. We want the data to be reviewed. Let's take a look. I know why. I didn't talk about electrolysis of water here. Why am I ahead? We have a copy of the CRC handbook. I'm going to bring it in. But every year it's updated and reviewed. So this is the 104th edition. That's what we're currently on. There's 104 years of the CRC Handbook of Chemistry and Physics. They update it every year to put in the latest data in here. It's a very thick book. So it's $170, so it's not that expensive. The price hasn't changed much over the years. That's the CRC handbook, and the other one is the Merck index. And these are considered reliable sources. Merck index is more for the biological chemists. And CRC is more for the inorganic and in physics. But this is chemical, drugs, and biologicals in the Merck Index. The Merck Index is pricey also. You can subscribe to it, but the book is pretty cheap. I don't know what the current edition is. It's updated every year. Wow, you can buy it for $7, but it's old. The 6th edition. '15th edition. Here's an example I wanted to just show. It's not just metals that conduct electricity. There are some non-metals that conduct electricity. Do you know a non-metal that conducts electricity? One of them is graphite. Graphite's an excellent conductor of electricity. And so here's electrolysis with a 9-volt battery using graphite electrodes rather than. So we take the water, we add a half teaspoon of salt. The salt will really speed things up in the electrolysis of water. And then this person's just going to use a couple of graphite electrodes in the 9-volt battery. So there's the graphite electrodes there. Let's speed this up since we don't have much time. And then there's a 9-volt battery. Let me speed this up here. And so this is a different thing. We're not looking at electrical conduction, but we're looking at hydrogen generation at this electrode and oxygen generation at the other electrode. And so that's graphite. Graphite's providing a conduit for the electrons itself. So we'll look at that again later. Okay, we'll stop here. We're going to continue this experiment next week. Thanks. See you tomorrow.
Oh, really? So that's something in your case or what?
I have a question about one of the questions on the exam. This one, number 34. Were you asking us to compare the different?
Keep my dinky until I realize.
A temperature increase of 100 degrees. 100 degrees, a temperature of 100 degrees is equal to 212 Fahrenheit. That's true.
Okay.
But if the temperature increased to 100 degrees Celsius, then the Fahrenheit didn't increase to 212. The reason is because they don't start at the same place. The Fahrenheit has a head start. And so the Celsius starts at 0, but the Fahrenheit had a head start at 32.
Okay.
Because these two are the same temperature. And so if this one goes up 100 degrees, and so now we're at 100 degrees C here,
Okay.
this one is at 212 degrees Fahrenheit because that's the boiling point of water. But the change isn't because they didn't start at the same place.
So it was supposed to be 32 plus,
Yeah,
The-
32 plus 180,
because that's,
because this goes from 0 to 100, and this would go from 32 to 212.
Okay.
So the change here is a plus 180, the change here is plus 100 degrees.
Okay, so you wanted us to like calculate the change.
The change, right,
Okay.
not the temperature.
The end temperature, the change.
The
that
change
would
in the
result in
temperature.
the same temperature
Yeah.
kind of thing. Okay.
Right, it
Okay.
would result in the same.
Okay, because that question had confused me. Okay, thank you.
Okay.
Hi.
Hmm?
Yeah, I used it, but I still need it for,
I have all
Next
three
week, too.
cards in there.
okay.
Yeah.
So you can just let me know which one.
Yeah, I'm just going to do the, couple more on this,
Okay.
and then I'm
I
done.
think it's back next week.
Okay, thanks.